Welcome to the 9th video in the Futura.tech Python package walkthrough. In this video, we'll be going through an example that presents the Causal and predictive market views and stress testing framework. So this is basically a combination of Bayesian networks and entropy pooling. It is arguably the most sophisticated framework that we have, but it's also the one that allows you to do the most interesting analysis. So hopefully after this video you will feel more comfortable with it and want to explore it further. So as always, we start at the front page of the repository and navigate to examples. And here you can see that example number 8 is called Causal and Predictive Framework, and this is the one that we'll be going through. But first, let's start by just exploring the article for this code. So basically, it's called the Causal and Predictive Market Views and Stress Testing, and if you just open it here in our browser, then we can go through some of the sections. And in recent years, causality has received significant attention in investment applications. So basically, this is both for us as humans to try to understand the world, but also as a way of trying to ensure that we don't overfit our trading strategies. So basically that we find something that works really well in history and then does not work in live trading afterwards. So this is some of the things that I mentioned here in the introduction, and then after that we start to present this causal and predictive framework. So initially we just introduce Bayesian networks, because most people who study finance and economics, they actually do not learn about Bayesian networks. They of course learned about Bayes' rule and Bayesian analysis, but combining it into this one network, it seems to be a new thing. So here we just introduce some of the terminology and the things that we need to understand how we work with them in this framework. So you can read about it here. Afterwards, we show you some of the mathematics that we will focus on the leaf nodes of the Bayesian networks. And basically the idea is to build a causal model on top, and then at the bottom we have the key risk factors of our portfolio. So this could be something like real rates, break-even inflation, and equity risk premiums, for example. And then this Bayesian network would help you to estimate the probability of the joint states for these risk factors that you define. And then finally you would use entropy pooling to take these joint states and then project them out into the market simulation that you have. So to really understand all this mathematically, you have to read it for yourself in the article, but I'm quite sure that if you read it carefully, then you will see that it actually is quite simple conceptually, at least. Alright, so then in this section there are some further perspectives, and this is basically telling you that in the way that we present the framework initially, this is in its basic form, but it's actually much more flexible than that. So you can, in the leaf nodes, have fully general entropy pooling views. And then we have some perspectives on causality and predictiveness, and also pointing out that actually the Bayesian network structure that you implement without specifying any realizations of the variables that you have in the network presents a view. So this is something that we will also see in the example a bit later. Alright, so then we get to the case studies, and in the case studies there are actually many different examples. So there are 4 in total, but this is just to illustrate that you can do so much with this framework that it is mainly our imagination that is the main limiting factor. We will be going through this example, the first one that we call a simple central bank Bayesian network. And here in this example we basically assume that the decisions of the central bank, they affect interest rate and implied volatilities. So yeah, and then you can see here we will see how we generated this plot for the different distributions on the different scenarios. Some of the other examples are related to top-down asset allocation. When I present something like this, when I talk with institutional investors, they are really excited about having the possibility to analyze their discussions in a quantitative way, and they tell me that this is exactly the things that they want to do. After that, we have some analysis with risk sentiment and equity bond correlation, also something that investment managers talk about in practice. And then finally, we have this market cases case study that you can read more about. All right, let's go back to the code and then look at the example. So in this example, first, of course, we import the package that we need, and then we note that we use this function that is called load risk factor. So this is a function that we haven't used before, but basically it's the function that generates or loads the risk factor simulation that we generated in the previous example, and that you can go in and then watch this video to see how that's done. So after that, we just extract this matrix R and then work with these risk factors again. All right. So here we build up the Bayesian network, and then in the Bayesian network, here in this case, it's quite simple, and so we can do it by hand. if you have something which has more levels and more complex than that, then you should really have some framework to do it, or some better interface to work with these things. All right, so in this case, we only have one root node, and this is the central bank one. So basically, we assume that the central bank can be either dovish, act as expected, or hawkish. You would have to specify what does this mean in terms of the risk factors afterwards. But first, we specify the causal structure. So this is the three states for the central bank, and then we say, all right. So for the interest rates, then we say if the central bank is dovish, then we say okay, then there's 50% probability that they will decrease rates, and 50% probability that rates will remain at the current level. So this is this is again something that you need to specify. What do you mean by rates increasing, decreasing, or remaining at the current level? And the same way here that we specify probabilities, if they act as expected, then we say that the probability that rates will go up, remain at the current level, or go down is symmetrical. And basically these probabilities that I've specified are of course just for illustration purposes. So I wanted to make something which is symmetric. In real world applications, you would of course work much more carefully with specifying these probabilities, with specifying the causality assumptions that you have, so you have full flexibility in relation to how you can do that. So here we compute the different probabilities that we need, so the different joint probabilities for the leaf nodes. You have to go through this code and then think about what actually happens here, but I think when you look at it, then you will see this is just a simple application of Bayes' rule. All right, so now we need to specify entropy pooling views, and as I said before, in this case we are working with the 1 month interest rate risk factor and the 1 month at the money forward implied volatility. So basically what we assume is that if you have a scenario where rates go up, well then this is the prior mean plus 1 standard deviation. If we have a scenario where the rates go down, this is the prior mean minus 1 standard deviation, and it's the same thing that we do for volatility. Again, this is of course just an illustrative way of doing these things. You can specify it much more precisely in real world applications. All right, so now we have just extracted the information that we need and specified the different right hand sides of rates and volatilities. So here we basically make a function where we compute this Cartesian product that is explained in the article. So you'll try, you have to read through that and then look at these things, because when you just look at it here without references to the article, it can be hard to see what is going on. But basically for the variables, we are trying to use the same notation as in the article, so you should be able to recognize these things. And then afterwards we just compute the different posterior probabilities. So basically we compute a posterior probability vector in the base case. So this is just if we have our prior market simulation, and then we say that now we believe that there are these causality assumptions. What does that do to our distribution without specifying whether the central bank is hawkish or dovish? And then the next one, we compute a posterior probability if the central bank is dovish and if the central bank is hawkish. So here we just show some statistics like the relative entropy and the effective number of scenarios, and this is just to assess just in the base case, how much of a difference is this the view that we have implemented? How significant a deviation is it from the prior? All right. So then we have implemented these posterior probability vectors, and now we want to have some portfolio that we can analyze. So of course, it's important to have a portfolio that has some sensitivity to interest rates and implied volatilities and things like that. And basically, in this case, we use the same portfolio as we did in the previous example. And you can here see that I even extracted the price manually of this put option that we priced in that example. So if you want to see more about these things, then I encourage you to go in and see the video before, where we also have to talk about this derivatives framework and why these portfolio weights still need to sum to 1, even though the exposures can sum to something else. All right. So now we have this portfolio P&L, and then we just make some plots. So the prior P&L, and then the base case for the Bayesian network, and then the dovish and the hawkish. So this is what you can see here. So you can see that when we have the prior distribution and the one that we call here the unconditional, just with the Bayesian network, it does introduce some changes into this simulation. And also, if you look in the case where the central bank decides to be dovish, then we can see that there is a shift in our probability distribution to the right hand side. So this is the case where we would have interest rates going down while implied volatilities also go down. And with the dependencies that are in this market simulation, it seems plausible that that our distribution will move to the right. And then finally, we see here that if you have the central bank, which is hawkish, then it's the case where interest rates go up, implied volatilities go up, and then even though we have this put option on the equity index, it seems that our distribution will shift to the left. So this is what it shows here. Finally, we just compute lots of different risk measures to see how the portfolios behave in this case. So this is what you can see here in the prior and the base. And you can see the difference between the prior and the base P&L simulation is not that large. So it seems that the views that we have implemented in this case, just the unconditional Bayesian network, does not significantly introduce new things that are not already present in the data. And then you can see that if you have this dovish or hawkish case, so you can see that in the dovish case, especially interesting, I think that you can see that the tail risks, they change quite significantly. So you have a much lower tail risk in the dovish case, while you have a much higher tail risk in the hawkish case. And I think this makes great sense, especially in combination with the plot that we saw of the distributions before. All right, so this is the walkthrough of the 8th example, and as always, if you like these videos, if you like this package, then I encourage you to give the GitHub repository a star, and then I hope to see you in the next video.